Hey, welcome to my new and improved way of doing my web help videos. I'm just going to take my already completed homework that I do every night, and I'm just going to go ahead and explain it. Okay, so for the first thing to keep in mind with all of this is in dealing with friction, the equation we're going to use is that the force of friction is equal to a multiplier, a coefficient called mu, which could either be for kinetic or static friction, and we're going to multiply it by the normal force, not the weight, but the normal force. The two are often the same, but not always. So let's see how we did this first one. Okay, so I now have a 45 kilogram box. So since it's a 45 kilogram box, I'll just draw a little quick FBD. mg downwards is 450 newtons, and since this object is at static equilibrium, it's not moving, I know that the normal force upwards must also be 450. So this right here, this value here, is what I use here for the normal force. Here is mu, which is 0.33, which is the coefficient of static friction, and that gives me 148.5 newtons. Now the box is set to moving, so now mu is going to be different. Kinetic friction is always less than or equal to static friction, so we want to find out what is the value of mu in the case of this situation right here. So I'm trying to find the value here. So the force of friction must be 99 because the box is in dynamic equilibrium. So if it's not accelerating, then I know that the applied force of 99 must also equal the friction force of 99. Otherwise, the box would be accelerating. So I say 99 force is how much friction I'm encountering. The normal force acting on the box is 450 upwards, and then I just solve it for mu, which is 0.22, which, as would be expected, is less than or equal to that one. Now this next one is tricky. Look at how we do this one here. Okay, I hope you can follow along with this one because this is a cool problem. Now I got the box on an elevator moving downwards. If the elevator is moving down, it's accelerating downwards rather, and I noticed that there's an error on this assignment. It's 2 meters per second squared is what yours says. So it's accelerating downwards this fast. So there, the first thing I've got to do is I've got to figure out what is the net force acting on it. Before we had it in static equilibrium where the downward force equaled the upward force, so the net force equals 0. But that's not true in this case. There must be a net force because it's accelerating. So our first job is let's find the net force acting on the system because we need to know what the normal force is. So always the net force equals the mass times the acceleration. The mass is 45 and the acceleration is 2 meters per second squared, which gives me 90. This is actually negative 90 because it's accelerating in the downwards direction. So now I just say negative 90, which I have here. Negative 90 equals the force of gravity plus the force normal, because remember, the net force is simply the sum of the forces. So if this is negative 450 in a downward direction, this is negative 90, what is the normal force? Well, it's 360 upwards. 360 upwards, 450 downwards gives me a net force of negative 90, which makes 45 kilograms accelerate at 2. Now, because I have a smaller amount of normal force, I'll have a smaller amount of friction force. So I take the normal force times the coefficient of static friction, and that gives me 119 newtons as the force of friction that I'll have to overcome to set it in motion. Let's look at this next one. I have 2 stacks of books. I have these three books here and this one here. So what I'm going to do is I make a free body diagram of the situation, sort of. And what I have here is I have 7 kilograms is going to produce 70 newtons of gravitational force, which is, since we're in static equilibrium, it's also going to give me 70 newtons of normal force. This stack here will produce 210 newtons of gravitational force, and since it's not accelerating, that means I have 210 newtons of normal force. So if I take the coefficient of kinetic friction, since the stack is moving, I'll take this number here and multiply it by each of these, which actually the normal force would be 70 times 0.15 gives me 10.5 newtons of friction force. and 210 newtons of normal force times 0.15 gives me 31.5 newtons of friction force. So now, in order to figure out the magnitude of the applied force, I just have to remember that since this is accelerating at 0.2, I can approach it this way then. I'm going to say I've got to figure out what the net force on the system is. Net force, as always, equals ma. So the net force on the system is going to equal the mass of the system, which is 28 newtons when I add all four of these together, times the acceleration of the system, which is 0.2. So mass times acceleration gives me a net force of 5.6 newtons in the positive direction. So now I'm going to say, well, the net force is also equal to the sum of the forces. So 5.6 newtons equals the applied force, that's how hard I'm pushing it, plus the friction force acting against it. And so I'm just going to say plus negative 10.5 combined with negative 31.5, which is negative 42. So then I just solve 5.6 equals Fa minus 42. The force applied must be 47.6. Oops, I forgot to put newtons here. Sorry about that. Oh, I put it here. Newtons. Alright, let's keep going here. Alright. The diagram above, the coefficient of friction is, oops, don't use that, Simpson, is 0.15. So the first thing I'm going to do is I'm going to figure out what the normal force is and use the normal force to figure out what the friction force is. So what I know is that the gravitational force is 600 because ma, 60 times 10 is 600. Since this object is not accelerating in a vertical direction, it must be 600 also. So the normal force is 600. 600 times 0.5 gives me 90 newtons of friction acting on this object. 200, which is the gravitational force and therefore the normal force here, times 0.15 gives me a friction force of 40. So what I find then is the total amount of friction acting on the system is going to be 90 plus 40, or negative 130. I'm pulling it this way, but I have 130 newtons of force acting in that direction. Now, if I want to find the net force acting on this, in order to find the acceleration, I have to find the net force acting on the system. I know what the mass is. If I want to find the acceleration, I have to know what the force is. Well, it's being pulled with a tension force of 250 this way, but it's also encountering negative 130 that way. So I need to just find the net force. The net force equals the sum of the forces. 250 plus negative 130 gives me a net force in the positive direction of 120 newtons. So now that I know what the force acting on the system is, I'm going to take that value here, and I'm just going to use A equals F over m. If I want to find the acceleration of the system, I take the force acting on it, which is 120 newtons, and I divide it by the mass of the system, which is 60 plus 20, and that gives me 1.5 meters per second squared. What is the magnitude of the tension on force T2? Well, now I know how fast the steel object is accelerating. It's accelerating at 1.5, so F equals ma, but it's F net. Now remember, this tension is not just accelerating this, it's also working against this amount of friction. So what I have to first do is find the, I'm going to say, what is the net force acting on this? The net force is going to be equal to mass times acceleration. 60 times 1.5 gives me 90 newtons of net force. That's what it's going to take to cause this object to accelerate this way at 1.5. However, that's not the tension on here. It would be on a frictionless surface, but I've also got 90 working against me here. So the net force, which is 90, equals T2 plus friction. So T2, which I'm looking for, plus negative 90, when I solve that I find it's 180 newtons. And I'm going to draw a free body diagram for each of these. So let's see what I've got here. Alright, now here's my steel object. We'll start with the gimmies. Alright, it's easy. 60 times 10, I get 600 newtons downwards. I get 600 newtons upwards since it's not accelerating in the vertical direction. Alright, now we've already established that there's 90 newtons this way, and we've established that there's 180 newtons this way, and those are all the forces acting on this. Now if you add these up, 600 and 600 in opposite directions gives me 0. 90 and 180 gives me 90. And if I say, it turns out that if you take 60 times this, you get 90. So I know I've done it right. For the box here, the wooden box, look what I've got. I know that the tension force is 250. I know it weighs 200, and therefore the normal is 200. Now the tension this way equals the tension this way. The tension on this line is the same in all directions. So that's 180, and I know the friction force is 40. And if I've done it all right, this box of wood is going to accelerate at 1.5. So if I add up the forces, 200 here, 200 here, that's 0. Positive 250, negative 180, negative 40. When we add those up, we'll find out that this object is definitely accelerating also at 1.5. All right. Oh, a crime scene investigation, or at least a traffic scene investigation. So the first thing I want to know is the force of friction acting on the car as it skidded to a stop. Well, the force of friction equals the coefficient of friction times the normal force. This car is on a level surface, we're to assume, so I can say 500 times 10 is 5,000 newtons of gravitation, and therefore 5,000 newtons of normal force. So I'll put 5,000 here. I'm told the coefficient of friction is 0.8. That gives me a friction force of 4,000 newtons. I'm going to draw a free body diagram. Here's my car. I have 5,000 newtons of gravitational force, 5,000 newtons of normal force, and therefore 4,000 newtons of friction force as the car moves this way. Now, what is the car's acceleration? Acceleration equals net force over mass. These two forces cancel out, so the only force I have to worry about is the frictional force. So I'll say 4,000 divided by the 500 kilogram mass of the car gives me 8 meters per second squared, which is actually a negative. It's slowing down. How many seconds does it take the car to skid to a stop? Well, let's see what I know. I know the distance the car went was 64 meters, and I now know how fast it's accelerating. So d equals 1/2 at squared would be my go-to equation. And when I solve d equals 1/2 at squared for t, I'll find it's 4 seconds. And then how fast was the car going when it began its skid? So now I'm looking for a velocity. So I think the best way to approach that would be with our big equation number 1. The final velocity equals the initial velocity plus acceleration times time. Now the final velocity is 0. The initial velocity is what I want to find out. And it accelerated at 8 meters per second for 4 seconds, which gives me 32 meters per second. Which, by the way, the car was speeding because he wasn't supposed to be going more than 25. That person's in trouble. And this is what these investigators actually do. All right. I'm trying to drive an ice sculpture, always a dicey thing to do. So let's see, what is the fastest the truck can accelerate? So the first thing I'm going to do is draw myself a quick free body diagram here. So the ice sculpture is 75 kilograms, so the gravitational force acting on it is going to be 750. Since it's not accelerating in the vertical direction, I can go ahead and say it must be 750 of normal force. 750 of normal force times the coefficient of static friction, 0.3, gives me a very minor frictional force of 22.5 newtons. That's all it's going to take to sit this thing sliding. So now, if I want to know how fast I can accelerate, acceleration equals F over m. The force of friction is what I have to overcome to set it moving, which is only 22.5. The mass is 75. So if I accelerate any faster than 1/3 of a meter per second squared, that baby's going flying. And let's see here. Alright, this is an old classic. A block of ice is sent across a frozen surface. How far away from the person, how far away from the person who shoved it does the ice come to rest? Alright, step 1. Do a free body diagram of the ice and determine the amount of friction force. So it weighs 250 newtons, therefore there's 250 newtons of normal force. 250 newtons of normal force times the coefficient of sliding friction of 0.02 gives me only 5 newtons of frictional force. So now this is a tricky problem, so let me just draw this for it. Not a free body diagram, I'm just going to draw it. Here's the ice. I know that it's going to go 8 meters. But then the trick is it's going to hit this sandy part, and it's going to go some unknown distance that I'm trying to find out. And so to solve this, really, I know it's going to go 8 meters. Ultimately, what I want to know is how far is it from here to here. But in order to do that, what I'm going to have to know is how fast is the ice going when it reaches the sandy part. So here's how I would approach it. The first thing I would do is figure out what is the rate of acceleration as this ice goes across here. At what rate is it slowing down? So A equals F over M. So here's the acceleration. The friction force acting on it is 5 newtons. It has a mass of 25 kilograms, so therefore it's slowing down at negative 0.2 meters per second squared. So what I'm going to do then is I want to say, well, how long does it take it to get from here to here? Because if it slows down for a certain amount of time, I can figure out how fast it's accelerating. So I'm going to say d equals 1/2 at squared, and I'm going to say it's going 8 meters. Half of a is 0.1. I solve it for t. It takes it 8.9 seconds to get to here. And now when it reaches this point here, I want to figure out how fast it's going. So the final velocity equals the initial velocity, which is 12, plus at. A is accelerating at -2, and the time is 8.9 seconds. So therefore, it starts off here at 12, and when it gets to here, it's going 10.22 meters per second. Now, it starts out going 10.22, and it's going to slow to a stop. But in order to find that out, I have to know what the acceleration is, which means I need to know what the force of friction is. Again, I'm going to do another free body diagram. 250 down, 250 of normal, 250 times the new coefficient of friction, and what that gives me is a frictional force of 87.5 newtons, because there's more friction now. So I'm going to say, to find the acceleration, I'm going to use Newton's second law, A equals F over M. 87.5 newtons of frictional force acting on 25 kilograms of ice gives me an acceleration of -3.5, which you'll notice is considerably larger than what it was before because the coefficient of friction went up. So now I'm going to use this kinematics equation. So it ends up at a velocity of 0. It started off at 10.22 meters per second. I'm going to square that plus 2 times the acceleration, which is -3.5, equals the change in distance. And when I solve that, I find that it goes 15 meters from here to here. So the total distance it went was 8 plus 15, which is 23 meters. That's a hard problem. Don't feel too bad if that one beats you. Okay, so what I have here is a 450 kilogram block being pulled downwards. I'm going to do a free body diagram of this. Oh, by the way, yours says 1,000. Alright, so let's get that one right. 1,000 newtons of upward. So I have 1,000 newtons of upward tension force. I have 4,500 newtons of gravitation down. The object is not accelerating, so therefore the normal force in this case, the force normal, must equal 3,500. And remember, it's the normal force, not the gravitational force, that determines the amount of friction involved. So I'm going to say 3,500 newtons times the coefficient of friction gives me 1155 newtons of friction force that must be overcome. So if I pull on this one with 1155 newtons, it will start to slide. Now if the cable breaks, what happens? Well, now what happens is I no longer have 1,000 newtons of tension force, so my normal force, instead of being 3,500, is now equal to the weight, which is 4,500. 4,500 times 0.33, it will increase to 1,485 newtons, which is a bit larger than what it was when I apply the tension to it. Now, what if the tension force was of 4,500 newtons? In which case, I would have a normal force of 0, and it wouldn't take, there would be no friction force to overcome.